Hey, welcome on the last lecture. Congratulations that you survived till this moment. The plan for today is to do some more examples, how to use flag algebras. And I would like to start with examples showing that you can use flag algebras not only for problems which are stated in terms of graph densities. Yeah, so till now, we were only solving problems which were to maximize or minimize some kind of graph densities, and our assumptions were also about some graph densities, right? This is the setting for flag algebras. But what one can do is sometimes you have a problem which is not stated in those terms, but you can define a different discrete structure which is already in these terms and use flag algebras for this structure. Let me do an example. There was a conjecture of Erdős, Andrzej, and Rousseau from '92 that if I have a graph which has number of edges at least n squared over 4 plus 1, so above the threshold, let's say it has exactly n squared over 4 plus 1 edges. So it's above the threshold for appearance of an odd cycle. So definitely it has some odd cycles. And the conjecture was asking if it means that at least 2/9 n squared edges asymptotically occur in C5. Why this number 2/9? So the conjecture was stated because what you can do is take a complete bipartite graph and attach to it a big tree touching just in one vertex. If I have such a graph, then what I can do, I can take this of size around 2n/3, and each of those of size around n/6. And now if you calculate the edges, it's around n²/4. Yeah, so by making your plus minus ones, you can achieve exactly this number. And now which edges do not appear, or which edges do appear in cycles in C5. So those edges occur in C5, right? While such edge never appears in a C5, because we have no way to close a 5 cycle using edge between those two parts. Yep. So when we count this is exactly 2/9 n squared, asymptotic, without looking at lower order terms. It occurred that the conjecture is wrong, because you can do better construction. And better construction is following. Take 4 sets, connect them by all possible edges between, like in the path, and in the last set, put all possible edges. So what I can do now, if I fix the sizes of the graph of those sets, roughly √2/4, around n/4, n/4, and here I need 2 minus √2, roughly. Yeah, it sums up to 1. Then what's happening? Those sizes are taken in such a way that the number of edges is roughly n²/4. And now edges that do not appear, or edges that do appear in 5 cycles are here between those parts, but those do not. Yeah, it's too far to close a 5 cycle. And if you count it, it occurs that 2 plus √2 over 16, and square edges are the green edges that appear in 5 cycles, and this is roughly 1, 3, 4 and square, which is a bit smaller. Yeah, so you can create a bit better graph. Okay, this was found and finally proved that this number asymptotically edges occur in C5 in our joint work with Pinghu and Jan Holec, and we do it using flag algebras. So when you first time see this problem, you may be surprised. Why flag algebras here? Like first, you need to say that your graph has exactly n squared plus 1 edges, right? Because if I forget about this plus 1, then there might be no 5 cycles at all. Yeah, so already this is hard to say in flag algebra language. And the second thing is even worse, how to say that this number of edges occur in a 5 cycle, right? Because it may happen that an edge is just in one 5 cycle, so it occurs in a 5 cycle, but densities of such 5 cycles is 0, right? It's just a single one. Yes, so this is not expressible in terms of graph densities. But there is a solution of this problem. So what we do is we consider not graphs, not standard graphs, but graphs with 2 colored edges. Yes, so let me use red and green. And I'm assuming additionally that edge which is colored red cannot appear in a 5 cycle. So in flag algebra language, it means that if I create a 5 cycle, then this density is 0. And by white edge, I mean it can be either red or either green. Okay, so whatever color I put here, with at least one red edge, then its density needs to be 0. Yeah, you understand? So what I want to say is I want to say that red edges do not occur in 5 cycles. Yeah, so green edges can appear, but the red edges are not. So densities of 5 cycles containing red edge is 0. Okay, this is basically saying that dividing the edges into 2 sets, those green edges and red edges, with green edges that can appear in 5 cycles, red edges cannot. And what I want to do now is state this problem following way. If I have sum of green edges and red edges, say at least half, so the density of those two is at least half, roughly n squared over 4 at least, then I would not be out. Okay. So proving this would be that what green edges, those that do appear in 5 cycles, times 8 minus 2 minus square root of 2 is bigger or equal to 0. Right? This would mean that edges that do appear in 5 cycles, their density is above 2 plus square root of 2 over 8, which means that they are above 2 plus square root of 2 over 16 and square asymptotic. Yeah, this is what we would like to achieve. Of course, it's not possible because with this assumption, I can have, for example, complete bipartite graph, which has no edges in 5 cycles. But what we can achieve is the following inequality. So it means if I have density of edges at least half, then the product density of triangles and this expression needs to be at least 0. Okay, and this we can do by flags. So this is standard application now. Maybe not standard because I have two colored edges, but everything works the same way. Yeah. Okay, so if it contains at least one red edge, then in its blow up, you will have a 5 cycle containing the red edge. Okay, so the density of those is 0. So basically, density of triangle containing at least one red edge also is 0. Okay, so we can do computations in flag algebras exactly as we were doing, but now in two colored edges and prove this inequality. And now how to finish the problem. So now I have two possible cases. Either density of triangles is above 0, and then this inequality means that this needs to be at least 0, and this is exactly what I want to achieve. Or density of triangle is 0, and this I can finish using some kind of stability, because density of triangle close to 0 with density of edges close to half means I need to be close to complete bipartite, and then we can finish it by some stability result. Okay, so what's the general lesson I want to give you is that if you have a problem which does not looking like a problem that can be expressed in graph densities, you can still try to solve it using flags by defining your own world with two colored edges, three colored edges, or some edges on vertices, whatever you want, and basically use flags for this discrete structure. Okay, is it clear? Let me do one more example of this type. I would like to show you now that using flag algebras, you can even solve problems like Ramsey numbers, which does not sound completely like a density problem. Yeah, what are Ramsey numbers? So Ramsey number of some set of graphs is the minimum n such that in every edge coloring of a complete graph on n vertices using k colors, there exists a copy of some of those graphs, so Gi in color I for some I. Yeah, you know Ramsey numbers, I assume. So for example, Ramsey numbers of triangle and, well, let's say all triangles, which means that if I color edges of a complete graph and k colors, there exists a monochromatic triangle in one of the colors. Yeah? Now, probably if I give you this as an exercise, you will be able to quickly prove it. Yeah, this is a standard graph theory course always. So using 5 vertices, you can color a complete graph of 5 vertices using 2 colors without a monochromatic triangle. And it's an easy exercise that if I use 6 vertices, click of size 6, then already I will find a monochromatic triangle. Okay? This completely does not sound like a problem on graph densities that you can use flag algebras. Yeah? We are not bounding any density of any subgraph. We want to find number of vertices. So either a fixed small number, like 6. Yeah? It's not graph limits. But still you can use flag algebras. This approach appeared first stating in a paper of Bernard Diewitzki and Florian Fender. So what they did is they defined two-colored setting, similarly as there, or not two-color, k-colored setting. But let me do an example. I will just prove this equality. So let's say this way. If there exists a graph on n vertices on n. And vertices so smaller than just if I take n, which is smaller than the Ramsey number, then there exists a graph which does not contain. There exists graph and the coloring edges, pale colors. Without copy of GI in color I. Right? So what I do from such a graph, I just blow it up. So for example, here, I blow it up. I will have 5 sets, and now edges are like and I can continue blowing it up. It creates some sequence of graphs, convergent as a limit. So what I can say about this limit, since it's a blow up of a graph, of a complete graph, if you take any two vertices which are not connected, so they should be from the same block, it's not possible that any third vertex is connected to one of them, but not connected to the other. Yeah, so this cannot be found in such a sequence of blowups. Yep. Also, this cannot be found in such a sequence of blowups. But also, it's not possible that two not connected vertices, so vertices from one block, are connected with some third vertex with edges in 2 different colors. Yeah, because I want them to behave the same to every other. Okay, so those 3 graphs do not appear in such blow-ups of those graphs. Yep. So what I want to do now, one more thing. I have n vertices here. So what's my edge density? Non-edge density. So in order to find a non-edge, both vertices need to be in the same block. Yeah, so here the density of non-edges is exactly 1 over n. Yeah, because I start with a graph on n vertices. So I have n blocks. You agree? Okay. So what I can do now using flag algebras, I can consider a world of graphs with 2 colors on edges, red and green, with additional assumptions that those 3 things do not appear. And also I don't have a monochromatic triangle. Okay, and in such a world, I want to minimize the density of edges. Yeah. So what's happening? So shall I write it? So for graphs without those structures, minimize the density of non-edges. And now, if I'm able to show, for example, in this case, maybe this one. Maybe let's say it differently. So let me minimize this and say that the minimum equals to some value, some delta. Like in this case, it's 1/5. Yes, I was thinking in general here. Yeah. Yeah, but in this case, it's 1/5. You're right. Yeah, so in general, if I take any graph on some number of n vertices, which is less than this Ramsey number, then I have such a graph and I can blow it up, and edge density will be exactly 1 over number of vertices in the starting graph. They started blowing up. Sorry, I don't want to minimize, I want to max. No. So let's say I run this program, setting those assumptions to my program, I minimize non-edge density, and I'm able to prove some lower bound. Let's say I proved that this is at least some value there. Okay, and what it means? It means no, otherwise, sorry. I want to show that it's at most. Yep. If I can find larger graph, then the edge density will be smaller. Yeah. So in order to say that there is no large graph, I need to say that the edge density the non-edge density cannot be too small. Yeah. So I'm trying to minimize. Yes. And if I'm able to prove some bound, then it implies that this Ramsey number needs to be at most 1 over delta plus 1. Yeah, why is it so? So if I'm able to, for example, in this case, if I'm able to prove that non-edge density is at least or strictly bigger than 1/6. Okay, if I manage to say that the non-edge density is strictly bigger than 1/6, then it means that there cannot exist a graph which is a blow-up of a graph on 6 vertices. Yeah, so there cannot exist a 6-vertex Ramsey graph. Maybe I need to stop a bit. Okay. I minimize my density of non-edges. I'm able to show a lower bound, at least some value delta. And what it means it means that there cannot exist a graph which has 1 over delta blobs. Yeah, because if there exists such a graph, then I would not be able to show such a bound. Yeah, and it means that the Ramsey number needs to be at most 1 plus the value here. Yeah, 1 over delta. Yeah, so in our case, I need to show that density of non-edges in this setting is bigger than 1 over 6. Yeah, because if it can be smaller, like for example, at exactly 1 over 6, then I would be able to find the 6 vertex graph whose blow up would not contain those graphs and would have non-edge density equals 1 over 6. Yeah, you agree? Okay, and now it's just the calculation. So in particular, Grzesik and Fender, they solved this, and you can find the exact calculation in the paper. So in this case, they just do n equals 4. So it generates all graphs on 4 vertices, which have 2 colors of edges and do not contain any of those 5 graphs. Just contain a label type, which is a colored edge in one or the other color, and one other vertex connected somehow. So this is the vector of flags that we will use in our computation, and just put it to the any SDP solver, and it gives that this is at least 0.17, which is above 1 over 6. And so the Ramsey number cannot be 7, it must be at most 6. This is what we want to show. Okay, I don't know if the idea is clear. Yeah, but basically, wrapping it up, if we are able to construct this Ramsey graph, so a graph is like coloring of a complete graph without those forbidden sets, then we can construct such kind of blowups with small density of non-edges. While on the other hand, using flag algebras, we can show lower bounds for the non-edge density, which is excluding having such a graph. Okay, and this way we are showing upper bounds on the Ramsey numbers. Some questions? Yes, in general, we'll have K colors. Yeah. So this is obviously known, but in their paper, they showed lots of different new Ramsey numbers using this method. Okay, I want to show you one more example, which is not of this type. It's standard density problem. But I want to show you that you can use flags not only to find a single point, I mean, maximizing some single density constraint, but you can find the whole curve. This is this differential method, or in other words, we defined graph limits. Or on the first lecture, on the very beginning, I showed you this analogy between graphs and graph limits. This is like rationals and reals. Yeah, and in real numbers, we can do lots of different methods. For example, we can do differentiating. So here you can also define something like differentiating a graph. And this gives a new method that we can use in our bounds. So let me now show you how one can do it. This was developed by Rasborov in his original paper on flag algebras. Okay, so let's move here. What's the differentiating, right? It's changing your value by a tiny bit, right? Changing argument of x tiny bit, and then looking how it's changing value of the function. Yeah, this is differentiating between it. So we want to do for graphs something similar. So we want to change graph or graphon a bit, just a tiny bit, and see how it's changing the function that we are optimizing. Okay, so what could be a tiny change that we can do? Now, for example, we can pick a single vertex and just remove it or clone it, make a copy of it. And now, what would be the change in our function that we are maximizing? So basically, we should count what's the contribution of the single vertex to the global function that we are optimizing, yeah, and see how it behaves. Let me do some example. So say that we are artificial problem, just maximizing number of cherries. Okay, and I have some extremal graphon, and now I would like to make a tiny change in this extremal graphon by picking some vertex, right? So I have now root there, and I want to consider cloning it, so making a second copy or removing it. If I do such a change, density of cherries in my extremal graphon should not change, right? Because if I'm able to make it bigger, then it couldn't be the maximal one, right? While if this vertex is contributing too small, then by removing it, on average, I will gain. Yeah, so the contribution of this particular fixed vertex should be the same as any other vertex in my graphon. So let me define something differentiating of a graph. I put one here, it will be explained a bit later. It does the same notation as Rasborov is using. So basically it's denoting that I'm removing or cloning single vertex. And by this, I mean, how is the density of a particular graph H changing by this small change? Okay, so if I take a cherry here, what could be the change? I should see what's the contribution of my vertex to the count of cherries. Yeah, so I'm counting all cherries that are containing my fixed vertex. It can be like this, but it can be also like this, right? And I want to compare it with cherry density in the rest. Yes, so because I'm saying that it cannot be away from what's happening in the rest. Yeah, if it's bigger, so the vertex appears in a bigger number of cherries than it's in the rest, and by cloning it, I will have a bigger function. While if it's less, by removing it, I will obtain a better graph. Yeah, so density of cherries, now I want to subtract it in the rest of the graph, is basically I look at cherry in the rest of the graph, so outside my vertex, and I completely don't care how this cherry is connected with my vertex, right? So since I don't care at all, I need to subtract all options. So it can have just single edge, two edges, or all three edges. Okay, everything else is symmetric. And because of some normalization issues, this is multiplied by the number of choices of the root in this graph. It's always number of vertices. Okay, let me do a different example. I want to find the contribution of edges, right? So I look at, now it's two vertices, how particular vertex is contributing. So it's contributing by this number of edges, right? This is the density of edges containing my fixed vertex. And I want to compare it with density of edges outside my rooted vertex. So I subtract all possible options. Okay. Now, why it may be useful? Yes, so say we want to maximize some function, some graph. Then the extremal graphon, which is realizing this maximum, needs to satisfy that this derivative is zero. Yeah, like the contribution of every vertex should be the same. And now this is quality that you can use in your programs, in your optimization, whenever you are trying to maximize something. It's tempting to just add to your program averaging this, that it's zero. Yeah, but the problem is that this is not giving us anything. Why? Let me do an example here. If you average this partial derivative of an edge, here I'm getting 2 times density of edges. Let me remove this. Then here, averaging this, we already calculated, it's 1/3 of this graph. Here is 2/3 of this graph, a cherry, and here is just a triangle, right? But we also learned on the second lecture that edge can be expressed as the sum of those 3 graphs with those coefficients. So this is exactly 0. Yeah, so assumption like this is not giving us anything. We already knew it. It's happening because this is like this part is average contribution of all the vertices except this one. And this is contribution of this guy. So if I average over all choices, then this is exactly the same as this. Yeah, but still, such assumption can be useful because what I can do, I can multiply it by anything. So any combination of rooted graph densities and then average. Yeah, and this way I get some new equality that I can use in my program. I will show an application a bit later, yeah, but intuitively, this is exactly what I was saying. So I calculate contribution to this graph in the rest, contribution by a specific chosen vertex, and I'm saying that it needs to be the same in the extremal graphon. Okay. You can do one more thing in a similar way. So this is not the only tiny change I can do to my extremal graphon. What else I can do? I can, for example, pick an edge and just remove it. Yeah, it's a tiny change. And I can calculate similarly what's the contribution of a particular edge. Yeah, this way let's do an example. So now I will denote this partial derivative with e as an edge. And let's say again that I start with a cherry. So now what I want to do, I look at particular fixed edge in my extremal graphon, and I want to count how I will change the number of cherries if I remove this edge. Okay? So how many cherries I will gain and how many cherries I will lose. So how can I gain a cherry by removing an edge? Yeah? It needs to be a triangle. And now if I remove this edge, I'm gaining a cherry. Yeah, so this is my gain. But I can never lose a cherry. If I have a cherry like this and I remove this edge, I'm losing it. Also, if I have a cherry like this, if I remove this edge, I'm losing this cherry. Yeah, so this is exactly how my cherry density will be changed when I remove edge between the two rooted vertices. And because of some normalization issues, this is also multiplied by the number of choices of the two vertices in my graph. Okay, so in general, you can define this for any graph, order 2, and now how many you will gain and how many you will lose. Yep. Okay, and what I can say, if I'm an extremal graphon, then by this change, I cannot gain, right? Because if I'm maximizing cherries, I'm doing some change, I cannot obtain a better graphon because I'm already in the maximum point. So what it means that this needs to be negative. Yeah, if I'm maximizing cherries, then I cannot have a positive gain. Yeah, and this is another inequality that you can use in your proofs. In general, no, and of course, you can also multiply by anything, but now you need to be careful because this needs to be non-negative, right? Because if I multiply by something negative, then I will lose the sign of the inequality. So if I multiply by any combination of graphs with rooted edge and average the combination which is non-negative, then I get inequality that I can use. Okay, so now think about general approach. So say we maximize some function of graph. Okay, I'm maximizing some function of graph densities. Okay, this is my problem that I want to solve. It can be some strange function. It does not be just a sum or single graph as we were considering till now. It can be really like ugly function. And say that this attains its maximum in some point A. Okay, and I want to assume that my function f is continuously differentiable. In some open neighborhood. Open neighborhood. Okay. Okay, so imagine you have some function that you want to optimize. Yes, and graph densities. I have some place where it's attaining its maximum. And what I want that in some open neighborhood around, this function f is differentiable and the differential is continuous. Yeah, so this way I can calculate partial derivatives of the function f. Okay, if I have this, then I can use those small changes and I can prove that it must hold if I calculate the partial derivative over each graph in the maximum point. And each of those I multiply by this partial derivative edge of this graph. So basically, this is saying how is changing the density of H1, right? And this is saying how the density of H1, change in density of H1 is changing the value of my function. So if I sum up over all those graphs, I need to have 0. Yeah, because when we are in the maximum point, whichever direction I look, and direction is density of particular graph, and I look at the change that the graphs that I'm gaining by this removing or cloning a vertex, I cannot gain or cannot lose by cloning or removing a vertex. So I really need to have 0. Okay. And I can do similar thing for the edge removal. So in this case, it would be that if I calculate the partial derivatives, in the maximum point, and now with those changes by removing an edge, I need to obtain something which is negative, or not positive. I cannot gain when I'm maximizing and I'm in the maximum point. Yeah, and this must hold for every placement of the root, like rooted edge, and every placement of the root. Is it clear? Some questions? So maybe let's pause at this moment, and after a short break, I will show you how one can use this to prove something. Okay, I think we can continue. So I want to show you a problem that was solved by Razborov, and it was quite loud. So what's the problem? The problem is very natural. Basically, for fixed density of edges, minimize density of triangles. Well, if the density of edges is less than half, we know that we can have 0 density of triangles, right? When we exceed half, some triangles need to appear. And the question is, how many triangles need to appear? This problem appeared already in the 50s in papers of Erdős. First non-trivial case was solved by Rademacher. That's why this problem is usually called by Erdős-Rademacher problem. So what we can say about it, for example, one of the exercises I gave you is to show a particular bound. Yes, is to show that triangle density is at least edge density 2 times edge density is 1. So if I started drawing it, say here is edge density, triangle density, up to half. We know that the minimum is 0. Of course, when I have edge density 1, I need to have triangle density 1. Right. And this bound is showing some curve. Okay. What we can say about it, for example, if I take complete by multipartite graph, balanced, if I take complete multipartite balanced graph, then this appears to be equality. So if I have 2 parts, it's exactly this point. When I have 3 parts, so my edge density is 2/3. It's this point, maybe I put. And I continue 4/5. It's this point, yeah, etc. So in those points, this is good answer. There are many such points here. But the question is if this is the good line or it's better line. And you can easily check that one can do a better line. Why? Like, the proof of this is just some Cauchy-Schwarz. If you did your exercise, you know how to do it. And you can observe that it's not possible to have equality for every density of edges, because the inequality that you are using is assuming that you are taking of every vertex the same. And this is possible only if I have a balanced multipartite graph. And the conjecture of Erdős and Rademacher was that between those parts, what's the best curve is just adding a small additional set connected with everything. Okay, so here I have just complete bipartite graph in this point. Then a third set appears, and together with the edge density it grows. And in this point, I will have 3 equal sets. Yeah, and then the fourth set appear, and it starts growing, and here I have 4 equal points. Okay, so this is the conjecture, but there are many improvements for this result. For example, Golobash proved a line segment. So Golobash proved that if you connect this by segments, then the triangle density is above those line segments. But this construction gives a curve which looks like this. And this curve is really not nicely looking. So let me write it just to show you how bad it is. So if my edge density is in such an interval, so the interval between 1 minus 1 over t and 1 minus 1 over t plus 1, then this function is saying that the triangle density is at least t minus 1. I'm not writing it so that you can write it down. I'm just writing it to show you how bad it is. Edge density and the square root and additional value. Squared and everything divided by t squared. Okay, so this is the conjectured optimal function. And now you can imagine how hard it should be to prove that indeed this is the best function. So what I want to show you is I want to prove this first segment. So I want to convince you that if my edge density is in the interval 2/3, then the triangle density is at least 1 minus square root 4 minus 6 times edge density multiplied by 2 plus square root 4 minus square and divided by 8. And so even in this first interval, the function is quite ugly. If you would like to express it as just densities of graphs, I mean, multiply like square whenever I have a square root, etc. It will be some huge expression on many number of vertices. Yeah, so it's not easy to express it as some nice linear function. Okay, but what happened with this problem is Razborov in 2008, he proved that the conjecture is true. So he showed this green line using exactly the differential method that I was showing you. Later in 2011, Nikiforov did exactly the same, but not for triangles, but for K4. And after him in 2016, Christian Reyer complete the problem for all cliques. Yeah, so he proved that the density of cliques of size K is at least some function of edges and provided the optimal function. Later, Kurko and Razborov showed in the triangle problem all extremal examples. These are not all, there are more. While Liu, which you know, together with Kurko and Staden, they gave an exact solution. So not in the density setting, but really for the number of edges and number of triangles whenever we are a bit far from the corner. Okay, so now how to use this approach? So I define my function that I want to maximize. This is a function of two graphs. Edge density and triangle density. Let me define this right-hand side by G so that I don't need to repeat it anymore. Okay, so as my function, I'm taking G edge density minus triangle density. Why this? Know that if I maximize this function, and I'm able to prove that the maximum is 0, then it exactly means what I need. Yeah, it means that triangle density is at least G function of edge density. Yep. So my goal now is to maximize this function. So we are in the setting there. So I have a function. You can check that in a, okay. And I want to show that its maximum is 0. Okay. So this function attains a maximum somewhere for edge density in this interval of 2/3 and triangle density anywhere. Yeah, so if I consider any of those, then this function needs to attain somewhere the maximum. This is a compact set. If the maximum is either for the density of edges 1/2 or 2/3, then we already know the answer, right? Because this is equality here, so we know that it works. It's exactly one of those two points. So assume that the maximum, f is in some point A, and it's inside the interval. So the edge density is in the open interval. Yeah, while triangle density is somewhere between 0 and 1, of course. Okay, so this is a one. So now, in this set, the function f is differentiable, and it's continuously differentiable. And so I can use the assumption there. So I have that the maximum is attained in some point, and in some open neighborhood of the point, my function f is continuously differentiable. So now I can consider those two tiny changes. So one change is just removing or cloning a vertex, and the other one is removing an edge. Okay, so I use what I did there. Okay, and first I remove or clone a vertex. And what I'm getting here, partial derivative over edge density. It's partial derivative of this. And this is exactly G prime. And this is multiplied by this partial derivative. This derivative with on a single vertex of an edge. Then I have partial derivative over triangle. Partial derivative of this on the triangle is just -1. It's minus, and then this derivative of the triangle. And this is. Yeah, you agree? This is exactly what I'm getting from the first assumption there. So what I can do with this, I can multiply it by anything. So I multiply it by a rooted edge. And this is the expression which is already using single root. So I multiply it by a single rooted edge and then average. Okay, I can do it. Now I need to write what it means. This is written here. So we know what it is. This is just a number, so I can take it out from the averaging. And now from this, I have twice. It's also here everywhere, so we take it out. And now I have averaging of rooted edge multiplied by there, and I have there a rooted edge also. So it's this. And I have there also edge density in the rest of the graph. And I multiply it by a rooted edge and then average. And this gives me, there is just edge density in the rest. And here after averaging, I get another edge density. So it's basically edge density squared. Yeah, so I obtain something like this from the first part here. Okay, and I continue. So differentiating a triangle. So using a similar definition, it would be 3 times triangle with a rooted vertex. Yeah, this is differentiating triangle. Like the first part multiplied by an edge, and average. And I have also there minus, so now it will be plus, triangle density in the rest of the graph, independent how it's connected with my root, multiplied by this and average. So from this part, I will get just edge density, and from that part, triangle density, and I have 3 always. Okay. So I got something like this. Yeah, there was nothing clever here. I just plugged the definition of this partial derivatives, and averaging where it was weak. Okay, now the second inequality. So differentiating on edge. Once again, I need to calculate partial derivatives of this function. I calculate it for edge, I get just g prime. And this time it will be multiplied by this differentiating edge. Right? This is this part. Okay, and now I do the same for a triangle. So partial derivative is -1, minus just partial the derivation of an edge of a triangle. This I want to multiply by, I can multiply by anything which contains a rooted edge. Yeah, because this is a rooted edge expression. So I multiply it by a rooted edge with a single vertex not connected to an average. And what I can say that this is at most 0, right? Because removing an edge between two rooted vertices cannot enlarge my function to the maximum. Okay, now I need to calculate this. Here, what I have, I need to count contribution. What can I gain by removing an edge in edge density? I cannot create an edge by just removing an edge, so it's nothing. Minus, I need to. Yeah, so there is no gain, but I can lose an edge exactly when I remove this edge between the two rooted vertices. So from here, I get just g prime of an edge times minus rooted edge. And this is multiplied by this graph, so it's just this graph. And then average, which is just removing the labels, just this graph. And the coefficient 1/3, because probability of finding an edge here is 1/3. So it's giving me this from this part. Okay, oh. Yes. And now this part, similarly, I cannot gain any triangles by removing an edge. So gain is 0, but there can be some loss, and I lose whenever I have a rooted triangle. So now it will be plus, and it's 3 times, choose 2, so it's 3. And here I have rooted triangle multiplied by this graph. So I got this equality. I will start. Let me subtract this inequality from this quality that I had. If I subtract it, I have g prime of an edge, which is multiplied by from here. This is this multiplication. That's 2. Yes. And here I have minus 1/3 of this. I've got here also this part. Let me write it like this. 3 times this multiplication. And 3 times this multiplication. Okay. I have also this part, so 3 times h times triangle. And what I'm left is this square. So I move it to the other side. So g prime h times h squared. Yes, I think I haven't lost that. Okay, now there are 2 simple calculations. So this thing we already calculated. I mean, we were calculating this multiplication. Right, this can be expressed in some sum of rooted triangle and rooted cherry. If you just calculate the thingy that I have here in the parentheses, then this will be exactly triangle density and edge density. This is just calculation. We were already applying such kind of calculations. While the thingy here, so this 2 multiplications, what's this? Here, if you apply those 2 multiplications, you have graphs on 4 vertices. Yeah, in each case. Graphs on 4 vertices, and each time there is at least 1 triangle. Because I need the triangle here and I need the triangle here. If you look at it, there are exactly 4 graphs on 4 vertices which contain a triangle. So I can write this as sum of those 4 graphs containing a triangle on 4 vertices with some coefficients. So I don't want to do it because it's just a boring computation. But if you compute it and compare coefficients, you can check that this is at least 2 times the triangle. And this can be also expressed in 4 vertex graphs containing a triangle, and really such inequality holds. So now if I plug those 2 things to the inequality I have, I obtain something like this. So from here I get just triangle times g prime h plus 3 times h minus 2. And on the other side, we get 2 times h squared minus h times g prime h. Okay, this sounds bad, but it's not so bad as it seems. Why? What we can observe on our function. And to be honest, I don't know how Rasborov observed it. But if you have a function like this, and you calculate its derivative, you can imagine it will be some ugly expression, but it occurred that this function satisfies for every x in the interval the following differential equation. So for x in the interval I'm considering between 1/2 and 2/3, if you calculate it, it's exactly this equality always. Yeah, this is just calculation. And since the function satisfies this equation, it means that if I divide by this, I get exactly triangle is at least, and this expression divided by this is exactly value of the function. Yeah, so this is exactly what I want. Okay, you may ask if this is positive because I'm dividing and not changing the sign of the equality, but you can check that this function has derivative which is at least 1, and this is bounded because I have edge density in specific interval, and indeed this is positive, so I can use it. Yeah, this way I end up in the inequality I exactly needed. So let me wrap up what we did in this problem. So I wrote my problem in the setting that I showed you of a differential approach. So just by maximizing some function of graph density, I wrote two assumptions, like two expressions. One is equality coming from copying or removing a vertex. And the other one is expression inequality coming from removing an edge between particular two vertices. In each time, I multiply by something to an average to obtain some inequality or equality. And then it was just calculations in flag algebra, just reordering terms in order to get inequality, which is exactly the inequality I needed because the function g satisfies this differential equation that appears. Yeah, and this is how Rasborov did this proof in the first interval. Later intervals are made in a very similar way, but it's a bit more computational. So I wanted to provide you only the first step. Are there some questions regarding this approach? One may ask why I was multiplying by this graph, not by something else. So note that this expression that we use means that removing an edge in my graph is not changing the value of my function. And I don't want to remove any edge that appear in my extremal construction. I want to remove something that does not appear, right? If I have some additional edges, then it would be good to remove them. And this graph indeed does not appear in this construction. And so it was quite natural choice to think about it. Okay. So in total, during those 5 days, I hope I showed you how to do calculations in flag algebra. So you are able to do the multiplication, averaging, and calculations like that. I showed you how to set up SDP solver so that its computer can solve whatever problem you have. I also showed you how to round up the solution so that you get exact solution. And I present you some applications, either for graphs, directed graphs, but also in the setting where the problem does not seem to be a problem for graph densities, but still we can use flags. I hope that it will be beneficial for you and useful, and you will solve some nice open problems using this approach. Thank you very much for this.